I would be talking about Magneto transport in topological states of matter. As you know, in the last nearly a decade, the topological states of matter have attracted a lot of attention, and it's one of the hottest fields in condensed matter physics. And last year, we had even the Nobel Prize awarded for that topic. These are states of matter which have unique surface states which are protected by the topology of the bulk. This may be a topological insulator or a veiled semi-metal, in which case there are points where veiled nodes where the bands touch, and that it also has a very unique surface state which is called as a Fermi arc. I will discuss more about it. And I will be talking about transport in this system, and in particular we'll talk about the role of defects and disorder in the way it influences transport, and we will also look at how magnetotransport helps in delineating some of the features. As you know, let me first start with the topological insulators, and we have, this is like a picture of a conventional insulator. You have the valence band, the conduction band, and surface states, and if you have system with strong spin orbit coupling, there can be a twisting of that, and because of that, the surface state, it is a metallic surface state. In short, a topological insulator is one which is insulating in the bulk, and it has a surface state which is conducting, and that surface state is spin polarized. It has the states have Dirac dispersion or a linear dispersion, and because it is spin polarized, the electron of this cannot be backscattered, and hence it has because of the spin momentum locking, backscattering is forbidden, and the electrons also have a Berry phase. The existence of this surface state has unambiguous evidence for that has been obtained from angle resolved photo emission, that there exists a linear dispersed state and that they are spin polarized. All this has been obtained. Now we have to see the signature of this surface state in a transport experiment, and that is if these exotic surface states, what is the transport signatures that they present. Okay. Now I will talk about the system which I am going to talk about is a prototypical topological insulator bismuth selenide, and let me mention about what are the challenges in trying to look for the surface or the features corresponding to the surface state. First is, this is a system bismuth selenide which is what they call as a quintuplet structure. It has a selenium layer, a bismuth layer, another different type of selenium layer, and bismuth selenium separated by a van der Waals cap. Okay, and this, when you take the spin orbit coupling into account, then it has that band inversion which I talked about. Now what are the challenges in seeing when you actually make the measurement of resistivity? It is conducting, for one thing. Okay, the transport is dominated by the bulk because of the presence of defects inside the bulk. Okay, the defect can be n-type doping or p-type doping and so on. They contribute the carriers. So the inherent thermodynamic defects are one of the contributing factors to the conductivity. The other aspect of contribution to the conductivity can come from band bending. The way the electron states which are at the surface due to something like a formation of a two-dimensional electron gas can also contribute to the surface state. So the issue is, if you look at a feature which arises a conductivity and you want to look at the conductivity due to the topologically protected surface state, then you have to discount or eliminate the effects of these. And here the magnetotransport becomes a very useful in delineating these topological surface states. Now how does a magnetotransport help in this thing? If you have the regular Shubnikov-de Haas-van oscillations as it is done in many of the metals and so on, then the oscillations in the conductivity as a function of B, if you measure, and the periodicity, as we all know, it is determined by the cross-section of the Fermi surface. If it is a three-dimensional this thing, it has this formula. For two-dimensional electrons with parabolic dispersion, then the cyclotron frequency goes as B, and this is the energy levels. So the spacing of this or the goes as n plus half is 1 over b. Now for the electrons which are Dirac dispersed, then this formula exists where the energy dispersion E is going as square root of b, and which leads to the spacing of these periodic oscillations has 1 over b, and that is no offset. So the position of the maxima in the Landau level plot can be used to distinguish between the quadratic and the linear. As I mentioned, there are contributions from the regular conventional two-dimensional electron gas, and if they have a parabolic dispersion, they have a certain spacing of the levels, and if it has a Dirac dispersion, it has a different spacing and different offset, and this can be used to distinguish. Okay, this is one feature. The other aspect in SDH oscillation is the strength of the oscillation is determined by the disorder, and this is given by the famous Lifshitz-Korsavich formula, where you have the amplitude decreasing because of the temperature effect, because of the disorder effect, and so on and so forth. There is also another aspect. Before I go to the result, let me tell you this thing. This was all about classical magnetotransport, and in the quantum regime, in the presence of magnetic field, as you know, the electrons will pick up an additional phase, which is the Aharonov-Bohr phase, and so this part of it leads to two effects. There is what is called as a weak anti-localization and periodic oscillation. In the case of if it is a disordered material, if the phase, the mean free path corresponding to the phase coherence is larger than the electron mean free path, then you can have interference, as you know, between the forward and the reverse path, and this leads to what is called as a weak localization. There is an increase in the resistivity. As I mentioned, in the topological insulator with spin momentum locking, there is a destructive interference when it comes back, and that is what is referred to as weak anti-localization. So when you apply a magnetic field, this weak anti-localization can be destroyed. So this is another aspect which we need to keep in mind. Now let me start about the results. As I mentioned, I will present the results on the bismuth selenide. We will look at what is the effect of defects, in particular the effect of selenium vacancies, and we have also done experiments on what is the effect of antimony doping at bismuth site or effect of tellurium doping at selenium site to look at the role of disorder. I will not present this result. Let me talk about, just to indicate how does the presence of selenium vacancy affect the transport. Here is the result of the resistivity as a function of temperature plotted in 3 selenium, all these are single crystals, plotted with selenium of 3 different composition. This is rich in bismuth, this is stoichiometric Bi2SC3, and rich in selenium. You find, first of all, you find a metallic behavior, and if you do Hall measurement, you find the carriers. This is inset shows the Hall measurement as a function of, and it has a negative slope. All the carriers are electrons, and in this case there is a small upturn also is seen in the selenium excess sample. So when you do the resistance as a function of magnetic field, these are the 3 samples where you have done resistance as a function of temperature. They look more or less similar, but when you do the magnetoresistance experiment, you measure the resistance as a function of magnetic field, then you find in the bismuth rich sample you do not see the oscillation. In the stoichiometric sample also you are not seeing the oscillation, but in the selenium rich sample you see clear quantum oscillations can be seen in the resistance as a function of magnetic field. Of course, the question is why? Why is this difference? And we have also done the Love pattern, and the Love pattern is the cleanest for the stoichiometric sample. It is slightly spots are bigger or disordered in the case of this thing, and here there are some streaking patterns are also seen. The question is why is the difference, or why is it that when you do magnetoresistance in the selenium rich sample, you are ending up with very clear signatures of oscillations and not so in the other samples. And In fact, this is the Fourier transform of this oscillation, which shows a very clear single peak corresponding. Now we do the positron experiments to look for if there are due to defects. It can be identified in a positron experiment, and these are the, as you all know, positron experiment. Positron is very sensitive to the presence of vacancies and so on. And so here are the lifetime measurement, positron lifetime measurement, and on the 3 samples of the bismuth-rich, stoichiometric, and selenium-rich sample. And what we find is the lifetime of the positron as a function of selenium to bismuth molar ratio. In the selenium excess sample, the lifetime is the smallest. Okay, and this is also the sample on which you are seeing the Shubnikov-D-Hassman oscillations. So to identify to understand why, what does this decrease in lifetime imply, we do the look at the positron density distribution, and this is the structure of bismuth selenide. Look for what is the region which is probed by the positron. Of course, in the case of a bulk crystal, as I mentioned, there are van der Waals gap in this between the quintuple layers. The positron prefers these open regions, and that is where it sits. In the presence of a bismuth vacancy, if you introduce a bismuth vacancy, the positron sits at the bismuth. And as I mentioned also, that there are 2 vacancies which are present. One is the 2 sites for selenium. One is the selenium which is at the van der Waals region, and one is the selenium which is between the 2 bismuth layer. And if you take the selenium, which is, if you have a vacancy for the selenium at the van der Waals gap, then the positron gets localized there. And if it is selenium in between, yes, it is the positron samples both the vacancy and this thing. So basically, you have the decrease in lifetime. I do not want to go into too much of detail. We have the experimental measurement. We can compute the lifetime. Based on that, we infer that the positron is the samples. This decrease in lifetime is due to the decrease of the selenium-1 vacancy. We can estimate the concentration of these from the measured lifetime, and these concentrations are of the order of 10 to the power of 17. Okay, so you just see small changes in the concentration of selenium vacancies or the selenium can lead to very dramatic differences, whether you see quantum oscillations or you do not see the oscillations. Okay, and I should mention there are theoretical calculations which also have indicated that vacancy in selenium is a possible candidate and so on. And okay. Now, all I said is we do not see the Shubnikov-D oscillation in the stoichiometric. What happens if you quench the sample or cool the sample at various rates? Okay, so these are the magnetoresistance measurement done on bismuth selenide, cooled at various rate, 1 degree per hour, 2 degree, and one much faster cooling rate. And now you see when you cool it fast, these are measurements of magnetoresistance measured with the crystal in the AB plane and along the C axis. Okay, so that you can look in both the direction. And what you see is, this is to get an idea. To see when you see this system, there are no oscillations when you see parallel or perpendicular. Here, when you cool it at 2 degrees per minute or at 137, then you see oscillations, no oscillations in the AB plane, but in the C axis, there is a very clear oscillation. So this also tells you that it is coming from a 2-dimensional, the oscillations come from a 2-dimensional structure of the electron. And you can estimate what is the Fourier transform, what is the frequency corresponding to, and so on. Okay. So what I wanted to say, magnetoresistance oscillation observed only when H parallel to C configuration. Now, if you take, for example, in the Bi2 SC3-1, then you see oscillations in both of them. This will indicate that there is a contribution both from the surface and the bulk. In this case, there is only contribution from the surface. Okay, and so this we can do now with the crystal, and so this provides a very a clear way of identifying whether the the electron state which contribute to the SDH oscillation come from the two-dimensional nature, or is it from a three-dimensional nature? We can analyze this nature of the SDH oscillations, and that we do by, that is, these oscillations, you can remove the background, look at the change in resistance as a function of 1 over B, and look at what is fit this to the Lifshitz-Kosovo equation and extract the Berry phase. Okay? Once you do that, then you get the Berry phase of 0.5. This unambiguously shows that the signatures that we have seen are due to the topological surface state. This is identified with that one. And you can also do what is called as a Landau level fit, and which also indicates that the I told you that dispersion will have n plus half in 1 over B. So this is the maxima and minima positions are plotted as a function of 1 over B, and from which you can extract the Berry phase. And this clearly shows that by controlling, you can get the signature of a pure topological surface state. Control of selenium vacancy is important. In a sample which is cooled at a rapid rate, we are able to observe the features of a topological surface state. Now, let me go to the other part on what happens if you introduce disorder. And the disorder part of it is by introducing tellurium in place of selenium. So these are the very, actually Bi2SC3 is an n-doped material due to selenium vacancy. Bi2Te3 is a p-type material due to anti-site disorder. There are calculations for that. So you can combine the two, whether we can get an intrinsic material that compensate the defect state, and with that several experiments are being done and have been done, and so we form compounds of we grow crystals of Bi2SC and tellurium of various compositions, all the way from Bi2Te3 to Bi2SC3, and look for what are the signatures. So, okay. So here are the X-ray diffraction pattern of the system we have is Bi2SC3TX. So X is being varied. So you have for X equal to 0, X equal to 1, 1.2, and what you notice is there is a change in the increase in the lattice parameter A and C, which corresponds to tellurium occupying because of the bigger site and so on. More importantly, if you look at the 015 peak, there is a broadening of the peak which occurs apart from the shifting, and that is indicative of the disorder which is produced when you introduce tellurium in place of selenium. This is also reflected in the Lavey diffraction spot, though not very clear, but there is a broadening which is seen. Now let's look at the resistivity behavior of this system in the tellurium doped system. We do the resistivity and Hall effect, and this was the Bi2SC3. You put tellurium further, then what was metallic starts showing upturn, becomes metallic, insulating type of behavior. The resistivity at room temperature also shows an increase with tellurium concentration. What we notice is that there is an upturn in resistivity with tellurium. If you do the Hall measurement of these samples, then you find these are Hall measurements at various temperatures from 4K to 200K as a function of B. In the Bi2SC3, you find it's a linear curve with hardly not very great change in the slope. And when you have higher composition of tellurium, then you see there is a non-linearity in the Hall behavior. The curve is, as at lower temperature, the curve starts to have indicate as if there are two carriers which are present. It has a non-linearity. Okay. So the nonlinear Hall behavior in this system suggests the presence of two carriers. Okay. Now we can analyze the combined resistivity and the Hall data and extract all the relevant parameters, and like the carrier density, you can get what is the mobility. So basically, and you can also extract the Ioffe-Regal parameter KFL. So what happens when you have the as you are increasing the tellurium content, okay, the carrier density comes down. It is more or less temperature independent. The mobility, while in the intrinsic sample is going up and it's very large, the mobility in the tellurium dome sample has come down. And if you calculate the KFL the IFL regal parameter, it is coming very close to 1 for the tellurium dome sample. So there is a strong amount of disorder in this sample. Okay, and so let's look at the way the magneto resistance behaves as you have changed. In fact, the decrease in the carrier density, etc., is somewhat surprising because Bi2 Te3 is a smaller band gap material. So one would have expected the carrier density to go up, but anyway, it decreases, and more importantly, the mobility also decreases. Now, if you look at the magneto resistance in this thing, this is the magneto resistance in the Bi2 SC3 system, which I had talked about earlier. That is, this is a